you will never reach another star. Not because it is too far, but because the universe will not let you. Right now, you are moving faster than you can imagine. The Earth spins, you orbit the sun. The galaxy drifts, and yet you feel completely still. Because your brain detects change, not motion. If everything moves together, you feel nothing. But zoom out, and the illusion collapses. Nothing is still, not planets, not stars, not galaxies. Even atoms vibrate endlessly. But here is where it gets strange. When physicists measure all motion, they get zero. Every orbit, every rotation, every spin cancels perfectly. And that should not happen. Now think about space travel. The fastest human object ever built moves at 430,000 miles per hour. At that speed, you could circle the entire Earth in under 4 minutes. You would cross the United States in 25 seconds. Yet reaching the nearest star would still take over 6,000 years. A journey that began when the ancient Sumerians first invented writing would only now be arriving. So, how far can a human actually travel in one lifetime? The answer is stranger than you expect. And it begins not with engines, but with time itself. Consider Voyager 1, launched in 1977, still flying, still sending data. After 47 years of continuous travel, it has covered 15 billion miles. That sounds extraordinary. Until you realize it equals less than 0.03% of the distance to the nearest star. If that journey were a road trip from New York to Los Angeles, Voyager would still be in your driveway. Visible from your kitchen window. After 47 years of non-stop travel, this is not a metaphor for drama. This is the actual ratio of distance covered to distance remaining. The problem is not engineering. The problem is chemistry. Every rocket ever launched burns fuel the same way the first fireworks did. Hot gas pushed backward. The reaction pushes you forward. Simple, elegant, and devastatingly limited. To reach 1% of light speed using chemical rockets, you would need a starting fuel mass larger than every galaxy, every star, every atom in the entire observable universe. Not Earth, not the Milky Way. Everything that exists. For a single small probe. That is what the mathematics actually demands. The universe has made the obvious approach physically impossible. Ion drives are more efficient, but their thrust equals the weight of a single sheet of paper. Nuclear rockets could triple our maximum speed. The nearest star would still take 28,000 years. Solar sails near the sun could reach 500,000 miles per hour. A whole lifetime of travel covers 1/7 of the distance to Proxima Centauri. You would die in the void between stars. Never arriving, never even close. Every propulsion technology humanity has built, tested, or can plausibly construct in the next 100 years falls short. Not by a little, by factors that make the word short seem generous. But hidden inside the physics that seems to trap us is a discovery made in 1905 by a 26-year-old patent clerk in Switzerland. He had no university position, no laboratory, no funding. He submitted a paper to a physics journal while reviewing patents at his day job. And in that paper, Albert Einstein demolished 3 centuries of assumptions about how the universe works. He began with one premise: the speed of light is the same for every observer, regardless of how fast they move. Whether you stand still on Earth or travel at half the speed of light, light always passes you at the same speed. From that single premise, he derived something that should have seemed impossible. If the speed of light must stay constant for everyone, then something else must flex to make the mathematics work. That something is time itself. Clocks aboard a moving spacecraft tick slower than identical clocks left behind on Earth. Not because they are broken. Not because of vibration. Because time itself flows at different rates depending on velocity. This is called time dilation. And it is not a theory. It is measured every single day. GPS satellites run faster clocks than Earth-based receivers because of their speed and weaker gravity. Without corrections for time dilation, your GPS would drift by kilometers per day. Every navigation you have ever done uses Einstein's 1905 equations. But for space travel, the numbers become something else entirely. Einstein introduced a number called gamma. The Lorentz factor. It tells you exactly how much time slows down at any given velocity. At everyday speeds, gamma barely differs from 1. The effect is real but microscopic. At 50% of light speed, gamma is 1.15. Your clock runs 15% slower than a clock on Earth. At 90% of light speed, gamma reaches to 0.3. For every year you experience, Earth ages 2 years, and for months. At 99% of light speed, gamma reaches 7. 7 Earth years for every single year of your life. At 99.9%, gamma exceeds 22 Earth years pass for every 1 year you age. At 99.99%, gamma passes 70 Earth years compress into 1 year of your personal time. Hold that thought, because this is where the impossible becomes nearly difficult. The star Vega, one of the brightest in the night sky. 25 light-years from Earth. At 99% of light speed, from Earth's perspective, the journey takes 25 years. But you are the traveler. And gamma compresses your experience by a factor of 7. You experience 3.5 years. You leave Earth. You arrive at a star 25 light-years away. Having aged 3.5 years. Push velocity to 99.9%. Gamma at 22 compresses that same journey to barely over 1 year of personal time. You could travel to Vega and return before your 2nd birthday aboard the ship. Earth would age 50 years during your round trip. You would age 2. This is not science fiction. This is what Einstein's equations require to be true. Now consider the twin paradox. 2 identical twins, Alice and Bob. Alice boards a spacecraft. Travels to a star 20 light-years distant at 90% of light speed. Bob stays on Earth. From Bob's perspective, Alice's outbound journey takes 22 years. Her return takes another 22 years. Bob ages 44 years waiting for his twin. From Alice's perspective, gamma at 2.3 compresses each leg. Her 22-year journey feels like 9.5 years. Her return, another 9.5. Alice ages 19 years total. When she walks back through the door, Bob's hair is white. Alice's shows the first traces of gray. They were born on the same day. They are now 25 years apart in biological age. This was confirmed in 1971. Physicists flew atomic clocks around the world on commercial airliners. The flying clocks gained time compared to identical clocks that stayed on the ground. Exactly as relativity predicted. The effect was tiny because airplane speeds are tiny. But the effect was real. Measured, confirmed. Time dilation is not a loophole. It is the operating system of the universe. And it transforms everything about what a human lifetime can actually reach. The Pleiades, that cluster of blue stars visible to the naked eye on winter nights, 440 light-years away. At 99.9% of light speed, the subjective journey time falls to roughly 20 years. You could travel to one of the most famous star clusters in human mythology, explore multiple stellar systems, and return having aged roughly 40 years. While Earth aged 880 years. Civilizations rise and fall while you make one round trip. The Orion Nebula, 1,300 light-years away, the most spectacular star-forming region visible from Earth. New stars being born, protoplanetary disks condensing into worlds. Planets forming in real time. At 99.99% of light speed, gamma past 70, you reach the Orion Nebula in roughly 18 years of personal time. You return having aged 36 years. Earth has aged 2,600 years while you were gone. The galactic center, the supermassive black hole Sagittarius, a star. For million solar masses of collapsed matter. 26,000 light-years from Earth. At 99.999% of light speed, gamma exceeding 200, a traveler could reach the gravitational heart of our galaxy in approximately 116 years of personal time. One person, standing at the center of the Milky Way, watching the black hole that anchors 400 billion stars. Push velocity to 99.9999%. Gamma exceeds 700, the galactic center, 37 years of personal travel time. A traveler leaves at 25, arrives at 62, one normal human lifespan. The entire galaxy within reach. Andromeda, the nearest major galaxy, 2.5 million light-years away. At gamma equal to 1 million, the subjective journey drops to 2.5 years. A trillion stars, an entirely separate island universe. Reachable while you age 2.5 years. Earth would age 2.5 million years during your journey. But you would arrive. The physics does not forbid this. The physics requires this, given sufficient velocity. But understand what time dilation costs. It costs everything that was there when you left. A round trip to the Pleiades at 99.9% of light speed. You age 40 years, Earth ages 880 years. Every person you knew is dead. Every institution you recognized has transformed beyond recognition. You return to the same coordinates and find a civilization made of people who share your DNA but not your memory. A round trip to the galactic center. You age roughly 74 years. Earth ages 52,000 years. The civilization that launched you has been gone longer than recorded history has existed. Relativistic travel is not transportation. It is a one-way door into the future of a world you can never return to. The farther you go, the more completely you sever every thread connecting you to the era that built your ship. This is the price the universe charges it fairly, without exception, for every traveler. Now consider the propulsion that might actually close the gap between where we are and where the equations say we could go. In the late 1950s, physicists asked what sounded like a deranged question. What if we detonated nuclear bombs behind a spacecraft and rode the shockwaves to the stars? Project Orion, endorsed by Freeman Dyson. Funded, tested. Actual explosions, actual pusher plates that survived them. The models flew, the physics worked. Political treaties ended it before atomic detonations could be used. But the concept was validated. A nuclear pulse spacecraft could reach 3 to 10% of light speed. Not enough for dramatic time dilation, but enough to reach Proxima Centauri in 40 to 140 years. Enough for a multi-generational crew. Enough to actually arrive. Antimatter propulsion sits at the theoretical extreme. When a particle meets its antimatter counterpart, both annihilate completely. 100% of their mass converts to pure energy. Not 0.1% like fission, not 0.7% like fusion, all of it. 1 gram of antimatter meeting 1 gram of matter releases the energy of the Hiroshima bomb. From 2 grams of fuel. The problem is production. Every particle accelerator on Earth manufactures roughly 10 to 20 nanograms of antimatter per year. An interstellar mission needs kilograms. At current rates, gathering that fuel would take longer than the age of the universe. Breakthrough Starshot takes a different approach. Leave the fuel on Earth. Use a ground-based laser array. 100 gigawatts focused on a grand-scale spacecraft on a gossamer sail. Accelerated to 20% of light speed in under 10 minutes. Alpha Centauri in 20 years. Photographs returned, the physics is plausible. The engineering is hard but not impossible. The limitation for humans, no brakes. The probe would flash through the target system and continue into the void forever. Fusion propulsion remains the most realistic near-term path. Project Daedalus, studied in exhaustive detail in the 1970s. Designed a fusion-powered spacecraft to reach Barnard's star, 6 light-years away, in roughly 50 years. 12% of light speed. Achievable with technology that could be developed this century. Not enough for dramatic time dilation, but enough to arrive within a human timescale. The harder question is bridging from 15% of light speed to 90%. That gap is the most formidable unsolved problem in propulsion physics. No known technology can build that bridge. But no known law of physics says it cannot be built. Now assume perfect propulsion. Unlimited energy, any speed instantly achievable. What then is the absolute limit physics itself places on how far a human can travel? The answer is not the speed of light. That can be asymptotically approached. The answer is the cosmological event horizon. The universe is not a static container. It is expanding, right now. Every galaxy beyond our local group is receding from us. And in 1998, astronomers discovered something that changed everything they thought they understood about the fate of the cosmos. The expansion is accelerating. Some unknown component of the universe, called dark energy, is pushing everything apart faster and faster. This creates a horizon. Approximately 16 to 17 billion light-years from Earth, space expands faster than any traveler can approach. Beyond that point, no matter how fast you travel, the destination recedes faster than you advance. Permanently and reachable. Of the roughly 2 trillion galaxies in the observable universe, only a small fraction are theoretically accessible before the accelerating expansion carries them beyond the horizon. The rest exist only as images. Light that traveled billions of years to reach our telescopes from places we can never touch. And this horizon is shrinking. Not staying fixed. Every year more galaxies cross beyond it. The window for cosmic exploration narrows with each passing moment. The universe is offering a limited time invitation. Here is the honest accounting of how far a single human lifetime can reach. At 99% of light speed for 50 years of personal time, roughly 350 light-years. About 50,000 star systems. Earth ages 355 years. You age 50 at 99.9% for 50 personal years, roughly 1,100 light-years. Millions of star systems. The Orion Nebula within reach. Earth ages over 1,000 years while you age 50. At 99.99% for 50 personal years, 3,500 light-years. The Eagle Nebula, the Carina Nebula. The Pillars of Creation. Earth ages 3,500 years, while you age 50 at 99.999% for one human lifetime, halfway to the galactic center and back. At 99.9999%, the entire Milky Way edge one person. One lifetime, the whole galaxy. At the theoretical extreme, where gamma reaches tens of thousands, Andromeda, the Virgo cluster, the large-scale structure of the cosmos itself. All fall within a single subjective lifetime. The universe has not designed barriers against exploration. It has designed a price list. And the price is everything you came from. Every person, every place, every moment of the world you knew. Everything stands, planets, stars, galaxies, even the particles inside every atom in your body carry intrinsic quantum spin. And yet when physicists add everything up, the total angular momentum of the observable universe is zero. Every clockwise spin is balanced by a counterclockwise one. Every galaxy rotating one way has a counterpart rotating the other. The precision of this cancellation across 2 trillion galaxies is one of the most unsettling facts in all of cosmology. And it matters more than it seems. Because in 1949, mathematician Kurt Gödel solved Einstein's equations and found something deeply disturbing. A rotating universe, one with any net angular momentum at all, would allow closed time-like curves. Paths through spacetime that loop back to their own starting point. Paths through which you could return to events already past. In a rotating universe, the arrow of time, the one-way flow from past to future that underlies everything we know about cause and effect, could break. The universe's total spin is zero. And now you understand why that might not be a coincidence. Our universe does not rotate. It keeps time clean. It keeps cause before effect. It keeps the future open and the past sealed. Perhaps that zero is what makes complexity possible. What makes chemistry possible? What makes life possible? What makes a person sitting quietly in a room feeling perfectly still actually possible at all? You live on a small rocky world orbiting an average star in the outer arm of an unremarkable spiral galaxy. Among 2 trillion other galaxies, separated by distances that make the word vast sound like an understatement. This fact is either the most isolating truth in the history of human thought, or the most breathtaking invitation ever extended to a conscious mind. The physics does not trap you here. The engineering traps you here. For now, the equations permit velocities that would carry you to places current telescopes can barely photograph. The barrier between your current existence and the life that spans the galaxy is not a wall. It is a speed, a specific, achievable speed, one that humanity does not yet know how to reach, but that the universe has never said we cannot. The Parker Solar Probe moves at 430,000 miles per hour. The threshold for meaningful time dilation begins around 67 million miles per hour. Between those 2 numbers lies every propulsion breakthrough humanity has not yet made. The universe built highways to every star in the sky, to galaxies so distant their light has been traveling since before the Earth existed. Every one of those highways is open. What we are waiting for is the engine. You are not still. You never were. The Earth carries you eastward at over 1,000 miles per hour. The solar system moves through the galaxy at 230 kilometers per second. The galaxy falls toward the Virgo supercluster at 600 kilometers per second. And inside every atom in your body, electrons occupy quantum states defined by their spin, their intrinsic angular momentum, their motion that never stops. The stillness you feel right now is not the absence of motion. It is the presence of so much motion, so perfectly organized, that the net effect at the scale of your body is the sensation of rest. Rest is not the bottom of the universe. It is one of its most sophisticated achievements. A temporary, local, carefully balanced illusion produced by the most restlessly dynamic system ever observed. You are not a still thing sitting in a moving universe. You are organized motion, complex enough to wonder where it all came from. Everything spins, every galaxy, every star, every planet, every particle in every atom in your body. And yet the universe taken as a whole does not spin. Every piece spins, the whole does not. That sentence is either the most elegant fact in cosmology or its most glaring open wound. Possibly both simultaneously. In the space between those facts, in the gap between the perfect bookkeeping and the absent origin story. Between the conservation law that holds everywhere and the initial condition it cannot explain, lies one of the deepest unsolved problems in physics. not a technical problem awaiting more precision. A conceptual problem about what kind of answer we are even entitled to expect. The universe has been spinning since before time had a name for itself. Every galaxy in the sky is a wheel that has been turning since before the Earth existed. Every atom in your body is broadcasting the signature of quantum spin quietly and continuously into a universe. That is, in some sense, made of the same thing it is announcing. We know how the universe spins. We know that it cannot stop. We know that adding everything up gives you impossibly nothing. And somewhere in that nothing, the universe has been carrying a question since its very first moment. A question the laws of physics, as currently written, are not structured to answer. The laws describe what happens to spin. They do not describe where spin came from. They keep the books with absolute fidelity across the entire history of the cosmos. But they have never shown us the first deposit.